which is simple stepwise reduction. So the first circuit we're going to start with, and we're going to continue to do some basics here, will be a simple series circuit. This is to remind you that at the same time that we're talking about stepwise reduction, I also need to start working in more and more of Kirchhoff's rules. So let's start with something relatively basic. Let's go 3 ohms, 6 ohms, and 18 volts. All right. I'm going to work on trying to make sure our numbers are easy in the beginning, but we all know resistors aren't going to come in values like this, right? Resistors are going to be like 22,000 or 150K. So I'll give us simple numbers in the beginning. The rules of stepwise reduction are the same as before. You reduce the circuit to bring it down to its most basic circuit form, a single equivalent resistance. And you do so by identifying series and parallel elements of the circuit. This one is no different. In this particular circuit, I can reduce it down to a simpler circuit that has a single equivalent resistance. And these are in series, so we just add them up. 9 ohms, 18 volts. This is our equivalent circuit. In stepwise reduction, yeah? Yes, sir?
Oh, no, never mind. I got resistors and capacitors.
I know you are. Everybody's going to. So please, stop doing that now. Start recognizing the resistor rules are the opposite of the capacitor rules. You're going to mess it up on the first test, so try not to. Believe it or not, on the equation sheet. Both of them. So, but they're in summation form. So if that's a problem for you, resistors in series. Right. Or maybe 1 to n. So that's what it's going to look like on your equation sheet. So summation form. Once you reduce your circuit down to its equivalent resistance, you apply Ohm's law this time. So V equals IR, or I equals V over R. Our job is similar to the job we had before, where we were trying to figure out the charge on the capacitor. In this case, we're trying to figure out the current passing through the resistor. But it's a very similar process. Solving a circuit is always going to be about figuring out things about the circuit. For capacitors, solving the circuit is about how much charge they acquire, and perhaps the potential difference across them. For resistor circuits, it's going to be how much current passes through them, and also the potential difference across them. In the capacitor side, we were doing that to figure out how much energy was stored. In the resistor side, we're looking to see how much power is being used by the resistor. But in the case of this circuit, we apply the 18 volts to our equivalent resistance. Recognize that we have 9 total ohms, which means 2 amps must be passing through this circuit. 18 divided by 9, 2 amps. Now, we could right now figure out the power consumption of the circuit, voltage times current. But while we're on this moment here, and we have a second to think about it, there's lots of ways to calculate power. If you're dealing with an ohmic circuit, meaning values that obey Ohm's law, then you can substitute and get other ways of calculating the power, working in resistance. So you do some substitution, you'll find that you can calculate power as I squared R. You can calculate power as V squared over R. These are just substituting in Ohm's law and finding other ways of calculating power. Just like with calculating the energy in a capacitor, we had 3 methods for that. There are 3 methods for power as well. This one, 2 times 18, 36 watts of power is being consumed by this circuit. All right. Now, as in the capacitor circuit, our job isn't done until we can break it down into the actual circuit we had before, meaning taking the information that's here and working backwards to apply it to our original circuit, step by step if we have to. First rule here, and going from an equivalent resistance back a step, when going to series, apply the current. resistors in series must have the same current passing through them. That's a consequence of Kirchhoff's second rule. There's no break in the wire, so the current has to be the same everywhere in that wire. So the 2 amps is passing through the 2 individual resistors. Again, series of resistors have the same current. Current's about charge. So remember, series capacitors had the same charge. It's a great simile there. Now, once you've applied the current, you can use that to figure out the individual voltage. 2 times 3, 6 volts here. 2 times 6, 12 volts here. Kirchhoff's first rule. Sum of the voltage drops has to equal 0. That has to be true here. 18 minus 6 minus 12 equals 0. Right? These two have to add up to the amount of voltage that was there before. Also, something a little more helpful maybe. If we look at the top resistor, it's consuming 2 times 6, 12 watts of energy. The bottom one, 2 times 12, 24 watts of power consumed. 24 and 12 equals 36. When you're done, unlike a capacitor circuit, this is important, unlike a capacitor circuit, you can add the individual powers and it has to equal the total power. In a capacitor circuit, you'd have to add the individual energies, and that would have equaled the total energy. It's a pretty good simile that for resistors, we're talking about power consumed, and capacitors, we're talking about energy stored. All right, a basic series circuit. Probably know what we should do next, and I hate to do this one because this one really doesn't provide us with much insight, but I think it appropriate that we do this one as well. A basic parallel circuit. Again, not a whole lot of insight here, but let's stick with our 18 volts, our 3 ohms, and our 6 ohms. Now, stepwise reduction, I have one parallel element. 1 over R equivalent has to equal the sum of 1 over R individual. So this is some of the inverses. Then invert the answer. If you forgot to do the invert the answer when we were doing our lab, that's why your numbers were so interesting. 1 over 3 plus 1 over 6. We've done this one before. Let's be reminded that when you're doing this, the total equivalent resistance for parallel is less than any of the individual resistors. But if you get a decimal value, something might be amiss. It's going to be less than the smaller resistor. Check it. But it's not going to be like 0.2 unless the smallest resistor is like, 0.3. Again, same idea here though. 18 volts, 2 ohms, 9 amps. That's a fatal amount of current, of course. Be careful. 1 amp is fatal. Stop the heart at least. Unlikely to penetrate the skin and give you that amount if you just grabbed a wire with 1 amp. 2 amps might, though. Now you're talking about like a defibrillator. They're around 2 amps. Now, we can take a look at the energy here, 9 times 18. I don't have that one off the top of my head. I'm sure you could.
It's 162.
Excellent. But traveling backwards, we're going back to a parallel element. I want to remind you, even though this one is relatively simple, it's the complicated ones that we're trying to apply this to. So when we go back to parallel, we apply the voltage. So elements in parallel have the same voltage. We kind of knew that for this circuit because both of these resistors are individually connected to the voltage source. But our next examples won't be like that. So I want to make sure that we have in your notes something that you can use. So that'll be 18 volts here, 18 volts here. 18 divided by 3 is 6 amps. And 18 divided by 6, 3 amps. It should not be too big a mystery that the total current passing through each leg should sum to be the total current that was in our equivalent circuit. The battery doesn't know whether there's 2 resistors or 100 resistors. It just provides current. All right. The basics. Any problem with this? Let's talk lab for just a minute. In your lab, you're asked to talk about the brightness of the bulb. Brightness of the bulb is power dissipation. I'll say it again. Brightness of the bulb is power dissipation.
Power dissipation.
Very good.
Oh, I thought you. I'm sorry.
What? I'm excited by your.
I sworn you wanted us to say it.
No, I am excited by your enthusiasm, though.
I was like, why am I the only one who did that?
Look, you made your best friend laugh.
Let's say, just for argument's sake, that the bulbs were 2 ohms each. Okay. In your circuit, you're supposed to take the 3 bulbs and connect them in series, and then take the 3 bulbs and connect them in parallel, and then create a circuit that had a combination of series and parallel. I would like you to do that real quick, algebraically. I'd like you to find the individual current and power consumption for a system that looks like this, where each of these resistors is a 2 ohm bulb, and we applied it to our 6 volt batteries. And then I'd like you to take the same path, but use a set that's in parallel. Again, 6 volts, each bulb 2 ohms. And then this one. This should make clear why you got the results you have. It should make it very clear. I want you to find power for each bulb in all 3 of these circumstances. This should not be hard. You should have no difficulty doing this. It'll only take you a few minutes. Yeah?
Isn't it relevant right now, but we didn't get to that lab?
Not everybody did. You will have to. I'm not doing it now. But probably in a couple days, there'll be an opportunity for you. We have another lab coming up.
This? About this? It's a good idea.
It would be fitting. Or, you know, if that's too long, you can bite.
One,
This is. This is 6 volts. 6 times 6 is 36.
Just like, use your dad's tools and like Jerry, booby trap your bike, make it have like thumb ID, so like only you can ride it.
But that's not what we did here. 18 divided by 3 is 6.
But like booby trap it too, like if you try to ride it without the thumb ID, like there's spikes coming out of the seat. Or like put 2 little metal studs on the seat and have the wrong person.
As I see it, no matter what skill level you're at, this is probably the amount of reduction you'd have to do. The first one, if you have 3 2 ohm bulbs in series, the total resistance, 6 ohms, with 6 volts suggests 1 amp. So, 1 amp, 1 amp, 1 amp, and that means 2 volts, 2 volts, and 2 volts, 2 watts for each bulb. Pretty straightforward. Not particularly hard, I hope.
5 to 2 watts.
2 times 1. Power equals voltage times current. All right. If I have 3 in series like this, go ahead.
Is it 2 watts for each of the resistors?
Mhm.
Or is it just like okay?
2 watts each, because the total wattage would be 6 times 1, or 6 watts, right? So I'd expect them to be the same amount. Now, you can reduce this one, but you don't have to. We know that's going to be 6 volts for each of these resistors. They're all in parallel. They all have an individual connection to the voltage supply. So you could reduce it down and figure out what the equivalent resistance is, which I think comes out to be, what, 2/3 of an ohm? You know, I'm not sure it's completely necessary. They're still 2 ohms each, right? Which means each one of them is going to have 3 amps passing through it. These bulbs are going to be bright. So what are we talking? 3 times 6, 18 watts per bulb, which if you connected those in parallel, you notice that they were all very bright. Now, the problem is that the battery probably couldn't provide the amount of current that you were asking of it. So as you probably got beyond 2 or 3 bulbs in parallel, they may have started to dim. But they shouldn't. If they had a perfect voltage supply, they should all got an individual current supply of the same amount. The problem is that batteries have internal resistance, which limits how much current they can produce. Now, this problem, where we have the parallel and series element,
Each one had 3 amps.
2 ohms, 2 ohms. You had to use stepwise reduction. This is our 2 ohm resistor here, but I took the parallel and reduced it. So I'm doing the parallel first. It's the only representation of a perfect parallel or perfect series in the circuit. So 1/2 plus 1/2, add together, you get 1. Inverse of 1 is 1, so that should be 1 ohm. Now I have 2 in series. 2 plus 1 is 3. 3 ohms, 6 volts, which means a total of 2 amps. When I work backwards, I take the current and apply it to the 2 bulbs that are in series. So 2 amps, 2 amps. And here's where I want to start getting a little critical about your thoughts on what's happening. 2 times 2 gives me 4 volts across that resistor. And then 2 times 1 gives me 2 volts, bless you, across that resistor. The voltage is not separated evenly. The larger resistance has the bigger voltage drop. This is not what we saw with capacitors. I'll say it again, the larger resistance in series will have the largest voltage drop. And it's not in a weird way. It is directly proportional. This resistor is twice as big as this resistor, so this voltage is twice as big as that voltage. It occurs in a perfect proportion. With resistors, the voltage is a percentage of the whole resistance. 2 ohms is 2/3 of the entire resistance. It's also 2/3 of the voltage then. That's why you get 4 volts. The 1 ohm resistor is 1/3 of the total resistance. So it got 1/3 of the total voltage. Resistors in series break up the voltage in a proportional manner. That's why a set of resistors in series is called a voltage divider. This is how you take say a voltage supply of fixed value and reduce it to something that can be used in your circuit. If your circuit needs 5 volts, but all you have access to are 6-volt batteries, and trust me, when you have nothing but double A's and they're all 1.5 volts, you tend to produce 6-volt sources a lot. Why do you think so many things in your life take 4 AA batteries, right? Provide 6 volts. And usually it doesn't take 6 volts. Most semiconductors start switching at 5 volts or 3.3 volts. So you choose batteries that are a little over what you need and you voltage divide them down to get the voltage you need for your circuit. So when you ask what's the purpose of these circuits, there's a purpose. Now, you may not know how your semiconductor operates, but you would use a resistor in series with your semiconductor to bring down the voltage to the necessary level. Now, once we've gotten here, we're going to take this back to the set that's in parallel. We take the voltage here, 2 volts, which means 1 amp and 1 amp. 1 amp plus 1 amp equals 2 amps, and it was 2 amps that was passing towards that system that was in parallel. The current was divided. Resistors in parallel divide out current. Now, this was 4 volts and 2 amps, so 6 watts. I'm sorry, 8 watts. Not as bright as these, but still pretty bright. 2 volts and 1 amps, 2 watts. 2 volt and 1 amp, 2 watts. This is why the circuit behaved the way it did. It wasn't just because it reduced the current. The brightness of those bulbs that were in parallel went down substantially because there was a reduction in current and a reduction in voltage. That's why they are so much dimmer than the one that was in series by itself. All right, you ready to go solo on this? These are pretty easy, right? Means you guys are good for, say,
Let's go.
holy moly.
You just have to simplify the circuit and backwards.
We have some names.
No, we don't. We don't get out of 34.
Oh, no.
Dad?
Can you do this one?
Okay.
Look, the idea is about reducing it and figuring out if you can get the voltages and currents to individual resistors. Pick one, you know, I don't care which one, but one somewhere on the inside. Can you figure out what the voltage and current is on that one? What? Equivalent resistance is 6 ohms.